thinking about organic chemistry and just chemistry in general, large parts of organic chemistry, consist of interactions between, lone pairs or negative charges and positive charges. I just realized I didn't start recording. Somebody else turned on the recording. Whoever it was, thanks. All right. Thanks, Cameron. No, you sit. Yeah. All right. So that's what I wanted to discuss is, a large part of organic chemistry. When we talk about it in the future, you're going to be talking about substances such as an oxygen with, we'll just say, right. Oops. So a substance such as CH3O- is going to be reacting with, I don't know, say CH3Br, and you're going to have a negative charge attacking a substance. This substance has a partial positive charge here, partial negative charge there, and you have reactions that occur like this, where you end up with, in the end, having CH3O, CH3 plus a Br minus. And I'm not expecting you to know this, but just try to get you to understand that you have negative charge is always attracted to a partial positive charge. So partial negatives and partial positives are always attracted to one another. So all of chemistry, most of chemistry consists of this positive-negative interaction that exists between molecules. All right. So I'm going to leave this and swap sides to number 17. Here we go. All right, chapter 17. All right, so we're a little bit behind in the syllabus, but there's a couple makeup days in the end, so we should be fine, be able to finish everything we need to finish. All right, chapter 17. We're gonna, talk about some additional aspects of aqueous equilibria. Right, you can see we've been talking about equilibrium now for quite a number of chapters. So guess what? Equilibrium is important. So recognize that. So let me get up my pointer here. Right, it says the effect of acetate on the acetic acid equilibrium. Now, if you recall, right, if we took acetic acid and we took it, and dissolved acetic acid in water, right, it's going to dissociate to give us protons plus the conjugate base, the acetate, molecule. Now, what happens if instead we take just the acetate molecule? If we take the acetate, and dissolve that in solution. So this is the acetate, and actually this acetate is missing a negative charge. Let me try that in. Oh, actually it's not missing a negative charge. Actually, it's got the charge, it's got the sodium in the beginning. So we're dissolving sodium acetate. So the sodium salt of the acetate molecule in solution, right? When you dissolve the sodium salt of the acetate molecule into the solution, you end up with, right, sodium ions plus acetate ions. So what happens when we mix these two together? And that's the question that we're going to be covering. Right. So if we take and add this acetate to the acetic acid solution, right, the presence of this acetate from the sodium acetate in an acetic acid solution is going to shift equilibrium to the left according to Le Chatelier's principle, right? So we have our equation, right? This is the acetic acid equation. And when we, just like we said in the previous slide, when we dissolve sodium acetate in water, we end up with more acetate molecules. So when we add sodium acetate to an acetic acid solution, we're adding molecules to the right-hand side of the equation. So Le Chatelier's principle says we're going to shift the equilibrium to the left-hand side, right? So when we do that, in order to shift the left-hand side, the acetate has to react with protons and it's going to decrease the number of protons in order to form more acetic acid molecule out in solution, right? So we're going to lower the proton quantity in solution, and we're going to thus increase the pH or make the solution less acidic when we do that. So this is known as the common ion effect. So whenever a weak electrolyte and a strong electrolyte containing a common ion are together in solution, the weak electrolyte ionizes less than it would if it were alone in solution. And this affects the acid-base equilibrium, obviously. So we'll also see later in the chapter how it affects solubility. So we'll talk about solubility later on. But right now we're going to focus on the equilibrium and the reaction. So we'll take an example. So this question says, what is the pH of a solution made by adding 0.030 moles of acetic acid and 0.30 moles of sodium acetate to enough water to make a 1 liter solution? Right. So we have our acetic acid solution right here, right? Our equation, and we have our Ka. We know the Ka of this equation, right? Ka is just products, right? Our products divided by our reactants. Products over reactants, and we got the Ka out of a table, 1.8 times 10 to the minus fifth. So what happens now? The question here is asking what happens when we add 0.30 moles of acetic acid and 0.30 moles of sodium acetate to this 1 liter solution, right? So in order to figure that out, right, we needed to figure out what our concentrations are. Now, recognize what we just did here. When we go from one slide to the next, we're showing molarities here. We go back to this slide. Remember that molarity is in moles per liter. So we have to take, right, we have our 0.30 moles of our substances, and we're dividing that by a 1.0 liter solution, which just equals 0.30 molar solution, right? So just recognize that there was a transformation that occurred between each of these steps, right? We had to convert the number of moles into molarity over here on the right-hand side. Even though they're exactly the same, that's because the numbers are made to be very simple because we used a 1 liter solution. If you had a 2 liter or a half liter solution, this number would be different. Anyway, so we have that here on the next slide. Let me bring up the pointer again. So we're simply going to be plugging in, right? We have our equilibrium, our equilibrium equation, and we have our ice table here, right? We know we're starting with a 0.30 molar solution of the acetic acid. We're also starting this time with a 0.30 molar of the sodium acetate, right? This is just like the last chapter we were covering some of those examples. Initially, we have no protons, right? So we know that when we're mixing this reaction together, we're going to have some type of a decrease in X of our initial concentration here to give 0.30 minus X. We're going to have an increase in X of both of the products. So we end up with an X for the number of protons and 0.30 plus X for the number of acetate molecules. So now it's just a matter of substituting that into the Ka equation, right? So we have our Ka equation that was a couple slides back. So we end up with the product concentrations divided by our reactant concentrations. Well, we could go through and do the quadratic equation here. It's going to be a little bit more complicated, but for this example right now, we're just going to assume that the X here and the X here, the two, plus X and the minus X are actually very small, so they're not going to affect the 0.30, right? They're not going to affect the 0.30 molar solutions. So what that simplifies, the equation simplifies quite a bit, right? So we end up with 1.8 times 10 to the minus fifth is equal to X times 0.30 over 0.30s, right? So these 0.30s are going to cancel, and then we're going to result with x equal to r, which is equal to the Ka, which is equal to our proton concentration. So I'll answer your question in a second, Sophia, about when you can assume when you can get rid of the x and when you can't get rid of the x for the quadratic equation, and you'll see why. But for this part of the example, right, we're with that assumption, we can make the assumption that here that the proton concentration now is just essentially equal to our Ka, right? Our Ka is in this case, and that's just because of the fact that we had 0.30 and 0.30. So we started with the same quantity of each of these in solution. So to get the pH, we're going to take the minus log of the proton concentration, which gives us a pH of 4.74. All right. So Sophia is asking, when can we make this assumption? Well, let's in the next this actually it's gonna be not this one. I'm trying to think of when there's one. Well, when we can make the assumption is because of the fact. Let me do right. So we can make the assumption because of the fact that our proton concentration here, right? The proton concentration, which is equal to x, because this x value is greater, it's greater than 5% difference versus the initial concentration, right? So if we took our 0.30, multiply that by 5%, right, then we would have, what is that number? I can't do any math in my head today. So it would be 0.015. So anything, if we were, if this solution was 0.015 molar, then we would have to do use the quadratic equation. But because of the fact that this is a smaller number than 0.015, we can make the assumption. Yes, it would be the reactant concentration in this case. All right. All right. So let's take a look at weak bases. Right. So weak bases work the same way. So the common ion effect applies to weak bases. It's the same way. If a solution contains a weak base, and right, a solution contains a weak base, and a salt of its conjugate acid, the base won't dissociate as much as if it is alone in solution, right? So we take a weak base, right, ammonia, right, the ammonia reaction where we take ammonia, we dissolve it in water, we end up with the ammonium ion and the hydroxide ion, right? So we're calling it a weak base because it produces hydroxide ions in solution. If we add the ammonium ion, right, add some ammonium ion to solution, this is going to shift the equilibrium to the left-hand side. And as that happens, we decrease the concentration of hydroxide, which is our base in solution. So simply by adding the conjugate acid of the base, we end up decreasing or lowering the basic concentration of the solution, which means we're going to decrease the pH, right? Because a higher pH is a more basic solution. So we're going to decrease the pH by lowering the hydroxide concentration in solution. So all you have to do is recognize that when we're talking about this common ion effect, right? We're talking about an acid, and I'll go back to the previous slide, right? Talking about an acid and its conjugate base, right? The acid and its conjugate base or a base and its conjugate acid. So whenever we're talking about the common ion effect, always recognize that you have to pair the two. It's going to be the acid and its conjugate base, or the base and its conjugate acid. So here's a sample problem. It says, what is the pH of a solution made by adding 0.30 moles of acetic acid and 0.30 moles of sodium acetate to enough water to make a 1.0 liter of solution? So we're going to go through and we're going to explain. This is the exact same problem we just covered. And hopefully everybody realizes this is the exact same problem we just covered, right? So we're going to go through and describe the solution in a slightly different way. Right? So first, when you're determining the pH of the solution containing mixtures of solutes, it's helpful to proceed by a series of logical steps. Right? First, you're going to consider which solutes are strong electrolytes and which are weak electrolytes, and then you're going to identify the major species in solution. Right? Next, you're going to identify the important equilibrium reaction that is the source of the protons and therefore determines the pH. Next, tabulate the concentrations of the ions involved in the equilibrium. And then fourth, use the equilibrium constant expression to calculate the proton concentration and then the pH. All right, so these are the steps you kind of want to follow when you're trying to solve a common ion problem. So we'll start first, because the proton solution, right? Because the acetic acid is a weak electrolyte and the sodium acetate is a strong electrolyte. The major species in the solution is going to be the acetic acid, which is a weak acid, the sodium ion, which is neither acidic nor basic, and is therefore a spectator in the acid-base chemistry, and then the acetate ion, which is the conjugate base of the acetic acid. Right? Right. Second, the proton concentration and therefore the pH are controlled by the dissociation equilibrium of the acetic acid. Right. So this is the equation we just had before. Acetic acid dissociates to give us protons plus the acetate ion. And then next, the equilibrium was written using protons rather than this is another point, right? This is something I've been discussing over and over again, right? We're no longer adding water, right? Water is no longer part of the solution, so we're no longer getting hydronium ions out, right? So we're taking off the training wheels. We're no longer showing the reaction with water to form hydronium ions. We're just simply showing that we have a dissociation occurring where the proton and the acetate ion are there. So just recognize that from here, on out, the textbook stops using water. All right. Third, we're going to tabulate the initial concentration as we did in solving the other equilibrium problems, right? So we're going to do the same exact thing. We have our 0.30 of each of the acetic acid and of the sodium acetate. And remember, this was because we had our 0.30 moles divided by our 1.0 liters, right? So that's how we got our concentrations here. And just like before, we had minus x plus x plus x, and we end up with our equilibrium concentrations in solution. So the equilibrium concentration of the acetate, which is going to be the common ion, is the initial concentration that is due to the sodium acetate, 0.30 molar, plus the change in concentration x that is due to the ionization of the acetic acid. Right, so we'll go through. We're going to use that same equilibrium expression, right? The same equilibrium expression here, right, where we have products over reactants. And we looked up Ka of acetic acid in a table. So we have the Ka. And that just simply is going to be right here, right? That's over in this part of the table. You can see our Ka is coming from a table. We just simply looked it up. All right, so the dissociation constant is you simply found in this table here, 16.2. You'd also, again, want you to make sure you look at Appendix D in the back of your textbook. You will have Appendix D appended to your next exam, so you need to understand what it's going to look like. In addition of sodium acetate does not change the value of this constant. So substituting the equilibrium constant concentrations from our table into the equilibrium expression gives us here, right? So here's our Ka expression, right? And we then therefore assume that x is small, and we remove the x just like we did in the last problem. So I'm not going to go through this in detail again. We solve for x, we get the exact same 1.8 times 10 to the minus fifth molar, and then plug it in to the pH equation, right? pH is minus log of 1.8 times 10 to the minus fifth, and we get our 4.74. All right. So this was just a slightly different way of walking through these steps. And the reason I did this is because it's going to be vitally important that you understand how to work through these problems, because this is the foundation for a lot of what's coming up. So comment in section 16.6, we calculated a 0.3 molar solution of acetic acid has a pH of 2.64, corresponding to the proton concentration of 2.3 times 10 to the minus 3 molar. Thus, the addition of sodium acetate has a substantially decreased the proton concentration, right, as we expect from Le Chatelier's principle. So all they're saying is, right, when we take this equation, right, if we just had acetic acid dissociating to give us our protons plus our acetate. Right, when we did this, ran this reaction, and if all we added was a 0.30 molar solution here, right, we ended up with a pH of the solution that was equal to 2.64. Right, our proton concentration here, our proton concentration is equal to 2.3 times 10 to the minus third, right? But in this example now, where we now have both have added both 0.30 molar of the acetic acid and a 0.30 molar of the sodium acetate, our pH now, right, is equal to 4.74, which corresponds to this proton concentration, which is equal to 1.8 times 10 to the minus fifth. Right, so you can see adding this additional acetate ion has a huge effect, right, on our proton concentration. Right, we're shifting the equilibrium very far to the left, and 2 orders of magnitude, right, from minus 10 to the minus 3 to 10 to the minus fifth, we're decreasing the proton concentration. Right, we're talking 100 times, approximately 100 times less protons in solution by simply adding a 0.30 molar solution of the sodium acetate. All right. Now I have a sample problem. So for those of you hopefully printed out, hold on, I need to do that. If you go to the sample problem here, hopefully you had a chance to print it out. If not, all right. Here's a sample problem. It says, for the generic equilibrium, HA is in equilibrium with H plus, right? HA is in equilibrium with H plus A minus. Which of these statements is true? I'll let you go through and read them, and when you come up with an answer, put it in the text box. Anybody have any questions? Answers, a variety of answers out there right now. I like seeing debate. Just think now, if a bunch of people haven't put any answers in yet, if you're bold, you can put an answer down. It doesn't make a difference. You'll be siding with somebody unless you're A. You want to be really different and go with A. All right. Let's think about what we're doing here, right? We have our equation. We have HA is in equilibrium with H plus A minus. Right? And then we're saying, so there's lots of different examples. So this is the equilibrium constant for this reaction changes as the pH changes. But we know equilibrium constants are never changing, so they stay the same. We can look them up in the table. So we know A is definitely not the right answer. Right, most of you got that. All right, so we go through B. If you add Ka to the solution of HA, that is at equilibrium, the concentration of HA would decrease. So let's see. If we take Ka and we dissolve that in solution, right? We put that into water, we end up with an equilibrium. I'm sorry, not an equilibrium. Dissociation. Right. We dissolve it in solution. We end up with K plus A minus. Right. So whenever we add Ka into solution, we know that a solution of Ka essentially exists as K plus and A minus. So what we're really adding to solution, right, is the A minus. The K plus is just a spectator. Right, it's just a spectator ion. So the K plus isn't going to have any effect on the reaction, right? So we're adding A minus into solution. So when we add A minus into this equilibrium, right, what's going to happen, right? If we add it into this equilibrium, this is, if we think of Le Chatelier's principle, right? Le Chatelier's principle tells us that the equilibrium is going to shift to the left, right? Right, and this is due to Le Chatelier's principle. So you're going to have the equilibrium shift to the left. So when the equilibrium shifts to the left, we're going to have an increase in HA, right? We'll see an increase in HA. We'll see a decrease. Let me use a different color here, maybe. Right. We have an increase in HA. We have a decrease in H plus, and A minus, because we're adding more, is going to increase, right? We're going to see an increase in A minus, right, because we just added a whole bunch. And so if we go through B, if you add the solutions, add the soluble salt Ka to a solution of HA, that's equilibrium, the concentration of HA is going to decrease. Well, because we shift the equilibrium to the left, you can see that that's going to be incorrect, right? Then it says C, if you add the soluble salt Ka to a solution of HA, that is at equilibrium, the concentration of A minus would decrease. Well, no, because we just added a bunch of A minus, so C is not going to be correct either. And it's going to be D then. If you add the soluble salt Ka to solution of HA, that is the equilibrium, pH is going to increase, right? Because if we're decreasing the proton concentration, and this you need to recognize, right, the pH of equal to 14, and then we have a pH equal to 1, right? pH equal to 1 has a high proton concentration, right? Whereas pH equal to 14 has a, oops, let me erase that. Oops, erase too many things. Right, this is going to be a low proton concentration. You can see here. All right, so if we decrease the amount of protons, right, when we decrease the amount of protons, we're going to decrease the concentration. So on the right-hand side, we're going to increase the pH. Questions? Does it make sense to people that now, after the fact? Right. Right. All right. Let's continue onwards. So next one, example exercise 17.2, calculating ion concentrations when a common ion is involved. So this question is going to ask us to calculate the fluoride ion concentration and pH of a solution that is 0.20 molar in HF and 0.10 molar in hydrochloric acid. All right, so now think about what this reaction is, right? We're going to have two different reactions going on in solution. So we're going to follow the same 4 steps outlined in the previous example, right? You consider which solutes are strong electrolytes and which ones are weak electrolytes, and then identify the major species in solution, right? So we'll do that in a second. Then we're going to identify the important equilibrium reaction that is a source of protons and therefore determines the pH. Then we're going to tabulate the concentrations of the ions involved in the equilibrium. And then fourth, we're going to use the equilibrium constant expression to calculate the protons and then the pH. All right, so we'll go through. So because HF is a weak acid and HCl is a strong acid, the major species in solutions are HF, H+, and Cl-. Right? So if you think about the major species, the chloride, which is the conjugate base of a strong acid, is merely a spectator ion in any acid-base chemistry. And then if we look at the problem is going to ask for the fluoride concentration, which is formed by the ionization of HF. Thus, this is the important equilibrium, right? The HF plus the H+, is in equilibrium. Right? So HF is in equilibrium with H+ plus fluoride minus. I'm going to, before we go on, let me draw in this one other equation. Right. Remember, one of the things they said up here is, right, HCl, it's a strong acid. We have complete dissociation to form protons plus chloride. Right. It's completely dissociated. So HCl is not found in solution. That's why when we were looking at the list here of things, substances are found in solution. HCl is not found in solution, right? We have HF because we dissolve HF in it. It's a weak acid, so weak acids dissociate to a small extent. You know, we're going to have protons, and the protons are primarily going to be coming from the HCl, and like I said, the chloride. And the chloride, again, is a conjugate base of this strong acid, so it's just going to be a spectator. It's not going to have any effect on this equilibrium here, right? And chlorine won't have any effect on the equilibrium here. All right. So the common ion in this problem is the hydrogen ion or hydronium ion. Now you can tabulate the initial and equilibrium concentrations of each species, right? So we have our starting with 0.20 molar solution of HF. We know that our proton concentration is 0.10 molar because that's the concentration of HCl that we have in solution, right? And then our fluoride initial concentration is 0. So just like usual, we have our minus X and our plus X's for the reaction to occur. And then we draw in our equilibrium, concentrations of 0.20 minus X, 0.10 plus X, and X for the fluoride concentration. So now it's just a matter, hopefully everybody sees this is just a repeat of everything we've been doing over and over again, right? We've just simply been going back and forth and just plugging in, creating our ice tables and putting our ice tables in place. So Katie, I just got a request. You're requesting control. There's something you wanted to present, or are you just playing with buttons? Maybe not. That's okay. Learning the technology just like you. So, all right. The equilibrium constant for the ionization of HF from Appendix D is 6.8 times 10 to the minus 4, and substituting the equilibrium constants into the equation, right? So we have our equilibrium expression, right? Ka is equal to 6.8 times 10 to the minus 4, is equal to our products over our reactants. So we just simply taking from the table and plugging in. I'm not going to be explaining this much more because this is just kind of should be common sense to you now because we've covered this plugging in to equilibrium expression over and over again. Right. Then we're going to make the assumption again. We're going to make our assumption that our x's are going to be eliminated. Right. We're going to assume that this x is going to go away. That x is going to go away. Because it's really small, we can double check in the end to decide whether or not we need to go back and do the calculation or not. But for now, we'll make that assumption. And that simplifies our equation quite a bit, right? Where we basically have half x is equal to 6.8 times 10 to the minus 4. So we simply solve for x here, and you can see that this x equals 1.4 times 10 to the minus 3 molar, right? So, and if we go back to the ice table here, we can say that x is actually equal to our fluoride concentration. So we automatically calculate our fluoride concentration. And, therefore, what the fluoride concentration is. So the fluoride concentration is substantially smaller than it would be in a 0.20 molar solution of HF with no HCl added. And the common ion, the proton, suppresses the ionization of HF, and the concentration of H plus is essentially the 0.10 plus X, right? So if we did, right, all that is 0.10 plus 1.4 times 10 to the minus third, right? Minus third. It's really bad, minus 3. Minus 3. So you can see essentially this small X concentration that exists is essentially non-existent, right? It's not going to affect the proton concentration. So you can see that this simplifies greatly so that the proton concentration is essentially equal to 0.10 molar, which gives us a pH of 1.00, right? So a 0.10 molar HCl solution dominates the control of the protons in solution, right? So our reaction, the pH of the solution comes solely from the dissociation of HCl, which makes sense. We're adding a strong acid and a weak acid into solution. The strong acid is going to be the key point for forming the protons in solution because the weak acid only dissociates to a small extent. And there's a comment at the bottom that says, notice that for all practical purposes, the hydrogen ion concentration is due entirely to the HCl. That's what I just said. So HF is essentially, right, the HF is only adding a 1.4 times 10 to the minus 3, which essentially has no effect or very small effect on pH. It would be out in the third, maybe fourth decimal place for its effect to be on pH. Questions on that before we do a sample problem? If not, let's do the sample problem. All right. Here's the sample problem. Sample problem says, calculate the concentration of lactate ion in a solution that is 0.10 molar in lactic acid, and it gives you the structure there. And the pKa and is 3.86 for lactic acid and has a 0.08 molar solution of HCl added. So there's a little bit of typo space, extra space in here. So now we have to go through, we're going to do the exact same thing. So take some time, work through. If you have any questions, post them in the box there. So think about what is the equation that we're looking at, the equilibrium equation. Draw out your equilibrium equation first. Yes, the concentration of lactic acid is 0.100 molar, correct. Anybody have any struggles they want to ask with before I go through? When you're ready, put your answer, A, B, C, D, or E. Waiting. Those of you who are still struggling to write the equation, so we have our lactic acid is giving us our conjugate base. Plus our protons. All right, then we just simply fill in our ice table, right? Which is 0.100 molar minus X. 0. I'm sorry, it's just 0 there plus X. So this is going to be X, and then our proton concentration is coming from the complete dissociation of HCl, right? So HCl completely dissociates to give us H plus or Cl minus. Right, so the concentration that we have here is the total concentration of protons that we have, which gives us a 0.080 molar plus X. Did everybody figure out how to calculate Ka? So what's your Ka equal to? Anybody? How do you calculate Ka? Anyone? Right, Ka is just the inverse of the pKa, right? Inverse log, which is just taking 10 to the minus 3.86. Right. Right, this is the inverse log. It's just 10 to the minus 3.86. Anybody get stuck on that point? Anybody want to admit to getting stuck on that point? All right, once you do that, you just simply calculate. Calculator should spit out 1.38 times 10 to the minus 4, which is rounded to 1.4, right, times 10 to the minus 4. At this point, you just kept plugging it in, then you're going to have the Ka is equal to your, I'm going to simplify right from the get-go to 0.080. I'm going to drop the X, right, times X divided by 0.100. I'm going to drop the minus X, right? So I've taken and decided to drop these two X's when I put them into the equation here. Right? So then you simply solve for X. Right? X is equal to 1.7 times 10 to the minus 4. And in this case, we know that that's equal to our lactate concentration. Lactate ion concentration. Right? So I assume because people didn't put the letters in, they were struggling somewhere along the way, maybe with the pKa. Is there anything else that I should need to explain through here? All right, so this is just E is your answer. I miss seeing everybody's face.
Can you hear me okay?
Yep. Go
so why did you, they said the pKa is equal to 3.86. And then they gave the molar concentration of HCl, but then you put the molar concentration of HCl under H plus.
Yes. And the reason for that is because HCl, right, if we have a 0.080 molar solution here, it's completely dissociated. So the concentration of HCl we have is the concentration of protons that we have. Right, in solution, we have a complete dissociation that occurs for HCl. So that gives us this H plus concentration is being poured into our solution. So that's where this comes from.
Okay, that makes sense.
Other questions? No other questions?
Wait, so it's more than 5
Oh.
per... Oh, wait, never mind. Never mind. I got it.
Oh, I see. My text box had stopped moving, so I just saw there were actually questions down. So pK is minus log of the proton concentration. Yes, Sophia, sorry. Unfortunately, my text box here was all messed up. So I thought no one was writing anything in, but they did. All right. So if you wanted to double check that the new concentration can be approximated as less than 5%, you would compare 0.1 molar or 0.080 molar. So you would, that's a good question. So you're going to be comparing it with the overall concentration of the pK of the, I see, if you're with either proton or, let me think about it. 0.08. You're going to be think about it in regards to the concentration of the 0.100 molar solution, because of the fact that the equilibrium expression is specifically for the lactic acid, right? And it's the dissociation of the 0.100 molar. Which would obviously, we're outside of that range. Yes. Curveball is the pK curveball thrown in there. Which is probably why you ended up with 4.83 molar. All right. All right, other questions? If not, I'm gonna go through and switch back here. Where are we from a time perspective? We have 5 minutes left. All right, so the last exams finally got in yesterday, so I will be grading, and I'll get those exams back as soon as possible now. So sorry for the delay right now. Hopefully it won't be like this in the future. Just everybody's traveling and all kind of the chaos of everybody moving around right now. All right. Buffers. So let's talk about buffers for a little while. So you've often heard about buffers. Kind of buffers are one of those solutions. They're, now you understand what a buffer is. It's a solution of a weak conjugate acid-base pair that resists drastic changes in pH. This is what we're talking about when we mentioned buffers. So now what we've essentially been discussing, like the acetic acid, sodium acetate solution, that's a buffer. We've just been going through the calculations, right? These solutions contain relatively high concentrations, right? 10 to the minus third or more, right? So remember, 10 to the minus third, right? 10 to the minus 2, 10 to the minus 1, right? You want large concentrations of these substances of both the acid and the base. You need both high concentration of the acid and its conjugate base. And their concentrations are approximately equal usually, right? And we'll explain why, right? So they give you some examples here, right? There are different buffer solutions on the right-hand side, right? There are various pHs, right? pH 4, pH 7, pH 10. These are the buffer solutions that are usually typically to calibrate the calibrate the different instruments that you need when you're measuring pH. So any type of instrument that you use is going to be that way. All right, what's going on here? Huh. All right, something popped up on the screen there. All right. How do we make buffers? So in order to make a buffer, we're going to simply mix a weak acid and the salt of its conjugate base, or a weak base and the salt of its conjugate acid, right? The same way that we look, working through the previous problem, we're doing the same exact thing here, right? We're weak acid and salt of its conjugate base. And then, essentially, right, we're going to have that means is we're just mixing, right? HA plus A minus, right? Or we're going to take the base, the A plus the HA plus, right? Right. So this is the base and its conjugate acid, or the acid and its conjugate base. We're just mixing these solutions together in order to form our buffer solution. The other thing that we could do is we could add a strong acid and partially neutralize a weak base, or add a strong base and partially neutralize a weak acid, right? So all that means is we have, right, strong acid. Oops. We're going to have a strong acid where this is now A is going to be a strong, well, let me use a real example. All right. We're going to have HCl, and we're going to partially neutralize a weak base, right? So you're going to react this with some type of A minus, right? And that's going to give us out in the end, right, our HA plus our A minus, right? All we did, and then we have the spectator ion, right, the chloride. This floats around in solution. So all this is doing is essentially swapping. Some of these protons are going to react with the weak base and give us our acid here and its conjugate base. All right. So how does a buffer work? So you could basically take a buffer. In this example, we're going to use a buffer of equal concentrations of HF and fluoride. Right. So if we add hydroxide to this solution, right, down here, right, our HF is going to react with the hydroxide. It's going to form water and fluoride, right? So what's going to happen is our HF solution is going to decrease, right? So we have a decrease in the HF solution that occurs. And when that, we can see we're forming more fluoride, so our fluoride concentration increases. But the key here, as you can see, is this change that occurs is very small, right? We have a small decrease and a small increase occurring. And then conversely, if we want to buffer it from, if we add acid to solution, right? When we add acid to solution, the fluoride is going to react with the proton that we add to solution. So we're going to increase our HF, right? So our HF is going to go up and our fluoride concentration decreases. Again, these changes that occur are very small. So our overall proton concentration that in the end remains the same, right? Because we have our HF reaction is in equilibrium to give us H plus, it's a really messy reaction here, H plus our F minus, right? So all we're doing is shifting the equilibrium back and forth from the left to the right. But our proton concentration, because these changes are so small, our proton concentration is very small. The change in proton concentration is always very small, which allows us to keep our pH nearly identical to where we started. So that's essentially how a buffer solution is working. All right, so we'll pick up here in the next class. Hopefully everyone has a good weekend. The problem set obviously was due. We finished chapter 16 last Wednesday, so make sure you're working forward on the problem set for chapter 16. Otherwise, have a great weekend. Relax, get some fresh air. Don't go play in crowds. See you later.